And I am very honored to introduce Professor Hirochika Inoue. Hirochika Inoue is a professor emeritus at the University of Tokyo. So during his 40 years of robotics research and development from 1965, as a graduate student to the university retirement as a professor in 2004, Professor Inoue explored a wide area of research in robotics, such as compliant control of robot actuations, real-time vision and also tactile systems for robots, planning, programming of robots, system integration, hand-eye systems, vision-guided vehicles, and recently, humanoid robotics. As a professor emeritus at the University of Tokyo, his experience and insight in robotics, research turned to research fundings, as well as support for robotized services in the future society. From April 2004 to September 2009, he was appointed as the Inspector General in the Japan Society for the Promotion of Science, and I would like to thank him for all the grants he provided to some of the French postdocs who came to GRL. So thank you, Professor Inoue. And his work and contribution are known, of course, worldwide. He is also a recipient of the JIRA Award in 1994, the Joseph Engelberger Robotics Award in 1999, the IEEE Robotics and Automation Pioneer Award in 2005, the IEEE, the medal with a purple ribbon, which is a very highly distinguished award in Japan, in 2008, given by the Emperor of Japan. And the French, we know this award. He is also the officier dans l'Ordre National du Mérite en 2010, qui a été donc attribué par le président de la République.
Discerned by the President of the French Republic.
Polytechnical Field Award that he got from the Robotics and Automation Society in 2011. So actually I know how Professor Inoue is viewed in Japan. So he's not only an inspiring researcher, but also a living school actually in Japan. So thank you to welcome Professor Inoue.
Good morning, everybody. Thank you very much, Dr. Keda, for your kind introduction. First of all, I have to thank Professor Jean-Paul Laumond to prepare this special opportunity to talk and discuss about robotics at the aspects of scientific and technological viewpoint. And today, I am talking about my lifelong challenge to create intelligent robot. My talk will be consisted of 5 parts. In part 1, I will introduce myself very briefly. In part 2, I will introduce my R&D at the university with my student. And in part 3, I will talk about humanoid R&D. And in part 4, if I have time, I will introduce some of my work at the national project for robotics. And in part 5, challenges to the future. I will propose some grand challenge for humanoid and robotics. So in part 1, I will briefly introduce my startup or my robotics life. 47 years ago, I was a graduate from Department of Mechanical Engineering, University of Tokyo, and entered into the graduate school. My thesis advisor suggested me to start some experiment about to build a mechanical hand and let that hand turn a crank. When I was heard from my professor about these topics, I did not understand what is the topics of it is. But I thought it seems very, very interesting. So I decided to start that topics for my graduate study. That is the beginning of my lifelong research of the robotics. And this is 5 years later, I completed, I am completing my doctorate thesis in 1969 October. This is a picture of my first computer-controlled mechanical manipulator system that has force sensing and touch sensing. The central part of here, pointer? Okay, no. The central desk seems a computer system. At that time, computer is very large, very expensive, and the performance is quite limited. Size is large, but the memory size is very small, and speed is also small. But using this, I have introduced this mechanical manipulator, which is developed for the nuclear power plant master-slave manipulators, and made some experiment. So this is an experiment of the task which I did in 1969. The computer is interfaced with the manipulator, and this hand stops when it senses of the touch. Okay, thank you. And using the tactile feedback, this robot can search and grasp correctly. And when I pull the block has no sense, but robot feels reaction force, and it releases after landing. This is also a same application to put stacking the object. Robot mechanical hand must release the object to checking it completely touch down or not. In such a way, very good stacking can be completed. In that time, the sensor is quite limited, about 18 tactile sensors and 6 degrees of freedom force sensors. So I think this is a prototype of the assembly tasks for robot. It searches and grasps the pin and pull it out, and to make sure it is completely pulled out, and then try to search another hole by sliding and feeding the reaction force, and it changes the shape and push into. So this is completely the first experiment to make the assembly tasks. And this is my young son. This turning crank is a very difficult task because the locus trajectory of the crank is quite defined by the machine itself. Robot must follow along to the constraint. So it needs a force feedback. This is a key point of the PhD study of my work. Yesterday, Jean-Paul said 50 years of robotics. He talked about industrial robot and 50 years ago and today. But I think intelligent robotics start from the 1956 Dartmouth conference. At that conference, McCarthy, Minsky, and others defined artificial intelligence. So I think it is the birth of the artificial intelligence. And in 1961, MIT Lincoln Laboratory, Robert did the TV camera interface to computer, and he made the first computer vision. In 1962, Ernst made computer-controlled hand. This is the first computer-controlled mechanical hand. And also, as Jean-Paul said, Engelberger introduced Humanoid in GM works. So maybe 50 years of robotics is counting from that. And in the topics of late 1960s and around 1970, that is the age of hand-eye system. MIT AI Laboratory, Stanford, SRI International, and Edinburgh University, UK, and Electrotechnical Laboratory and Hitachi, Japan, and 6 groups competed to develop the hand-eye systems. The people who is doing research on intelligent robots is quite limited. So maybe the people who is doing this research in the world is less than the people attending today. So I know almost everybody who is doing where and so on. And my robotics life start from this 1965 and coming to the 2004 to the retirement of the university. And this is a curve of the Japanese economy growth. When I was graduated, the GNP is 75, something like, and right now about 50. So during this 20 or 30 years, it doubled about, it becomes 6 times. After then, almost flat, and now decreasing. So society changes very much. The robotics research and actual application to industry is along this area. The very rapid growth of the Japanese economy is almost corresponding to the development of industrial robots and so on. So I am going to the part 2. Robotics is a study on intelligent connection of perception to action. This definition is done by Sir Michael Brady when he started the first ISRR. That is about 25 years ago, 1983. So more than about 30 years ago. So I like this very much. Yesterday he said intelligent connection of sensing to action. But I think is action to perception and so on. So along this idea, my study in the university environment is done by the 4 pillars. One is the manipulation study, second one is the robot vision and hand-eye systems, and third is vision-guided mobility, and fourth is the system integration and intelligence. I think robotics most interesting thing for me is to make the science of integration, to combine perception, action, intelligence, user interface, everything must be integrated into a single system. For that purpose, I have tried many challenges with my students. In the university environment, not myself, but as Mike yesterday said, that is creativity drivers, creativity engine. And it is very, very happy for me to have a very good student. And so, manipulation studies, I did many kind of things. For instance, precise assembly of 1,000 inch clearance, and torque drive manipulator, parallel manipulator, and so on. I will show some examples when I was staying at MIT in 1973. That is the assembly task of very simple, very close clearance. So this is the robot system interface to PDP-6 computer that is connected to PDP-10. And that is a very good research environment for me to create it. The method to do the assembly task almost similar to my PhD tasks. PhD work, but this is much more precise. And I enjoyed it very much, the stay at the MIT, and enjoyed this very much. Though when I returned back to Japan and moving to university, I decided to every program must be written in my laboratory. So in such a way, this is very precise assembly tasks. That is, I think, for the one of the results is Professor Minsky at that time made a mini robot proposal to DARPA that defined, that declared thousands of inch assembly by robot, but nobody did it. So I tried. I have a good chance to do it. Okay, so far, most of the compliance and force feedback is done by the torque sensing and force sensing. But another new challenge is to create a completely new machine that is all of the joint is controlled, torque controlled systems, not position-based one. This is some example like that, and the smooth operation in the systems. So I have to hurry a little bit. This is another interesting operation. Without grasping object, we can change the posture of the object. The tumbling, sliding, turning, in such a way. This is very efficient motion, not only for manipulating very small objects or large objects like furniture. In that time, some part of the gravity is supported by ground, and just a few small force is necessary, is needed to change the posture. So, second pillar is robot vision and hand-eye systems. Hand-eye system, the emergence of the hand-eye system is around 1970. But when I moved from electrotechnical laboratory to university in 1978, I started to build a very small laboratory. All the walls must be painted like Mike said, and this is a very simple hand-eye system. The vision system and a manipulator is this is a computer system, and all my students is engaged in their study using this system. Somebody is concentrating his effort to vision system, others manipulations, and others also the intelligence planning and so on. So using those activities, we prepared a system, Cosmos, a platform to accumulate cognitive sensor motor operation studies. So every year, every month, every week, the activities of my laboratory is concentrated and integrated into this system. And the first experiment, this is the tying a knot. Professor Inoue, at that time, he was a student of myself. He tried to make the stereo vision systems and to recognize the position of the rope and to find the hole and to make it and turn a crank. In that time, we have not much money, so I mirror assembly made the stereo vision system. Time is very slow, but anyhow, I will start. Right now, everybody carries the digital cameras, and the performance is becoming very much, and taking the picture and processing, retrieving, changing of the image is very, very easily done. But 30 years ago, it is very, very difficult to get the computer-mated vision systems. Before doing the vision hand-eye system, at first, we have to build our own vision systems. So I also tried to check, tried to develop some of the vision systems, that is the stereo vision system and the shape recognition and depth and so on. In such a way, every vision system must be connected to the manipulation studies. I think computer vision system pursues the precise recognition and representation of the object. But for robot vision, it is very important to make the feedback in real time. Therefore, some local high-speed vision is needed. Also in 3D. So we developed many kind of vision system. But I have to skip a little bit to talk everything of my plan. So the third is the vision-guided study. We have developed many vision-guided robot systems. This is a stereo tracking vision system is put on the mobile robot. And it is detecting the people is moving and object recognition, and also this is also the scooter system, which computers and the steering system and the stereo vision system is put on the senior citizens wheelchairs. And this guy built this system and doing the experiment on here. That is about 15 years ago, and their car is coming, so he forced to stop. Maybe drivers surprised that. And this is also another kind of the mobilities. The technique which is used for controlling locomotion, that is also the vision-guided motions. I have to skip. The fourth pillar is the system integration and intelligence. So the mobile robot with vision, manipulation, and AI, and teach a robot how to handle objects by showing task demonstration, and also remote brain approach for software R&D. So I will talk a little bit. This is my first build of the totally integrated robot system, mobility and manipulators and the TV cameras here. This is a fiber scope here, and this is the lens. Look down here, and this is a tactile sensor over there, and the manipulators, the vision systems, and mobility, tactile sensors, and this is connected to the large computers for making the intelligent system. So using this, we have tried many demonstrations. This is Professor Kuniyoshi now. He is showing his assembly task in front of the vision system. And this vision system recognizes what kind of assembly task he is doing, and recognizes making a plan and to turn it into the real program. That means let's show some operation in front of the robot vision, then teach what should be done. This is a very interesting approach, which is done by Professor Inoue. He is a successor of my laboratory. When he was the young professor, he proposed this remote brain approach. That is about 20 years ago. The robot consists of brain and body. Body is a machine to be controlled. Brain is for robot brain is a computer. Usual design. In usual design, computers put on the machine inside, but by the limitation of the size and the weight and so on, the computer performance is quite limited. Dr. Inaba does not like this kind of limitations. So he considered to link this robot with the computer by the wireless. This is just only the wireless servo systems, and the computers and wireless servo system is linked to the wireless, and the vision system is also linked to the wireless. So using this, the brain is placed on the remote place. So he said, remote brain approach for intelligent robot. This is quite a good approach for the study of intelligent robotics, because the size of the program is not limited to the computers on board. So supercomputers is used to make the recognition, the intelligence, and the database, and then the result is transferred to this. Using this, many kind of robot is done. This is 4 degrees of very small robot system. And this is for servo system, wireless servo system. Is no computer here, but it is maybe the first, just only one robot that can turn and no problem to turn over. It can change and turn, and usually so. Another approach. Oh, sorry. This is this robot, the human-shaped robot, very small one. Do not afraid to fall down. Even to fall down, it can stand up. Therefore, it is very good to do the experiment of such. When I show this movie to some small children, he asked, does this robot feel cold? But this is just a noise. And also this is the vision-guided motion control, the swinging operation, to make to get the timing to accelerate the motion. The vision system is here, and look over something. And according to the motion of some target, this robot can identify in what time they can move it. Okay, I have to move to part 3. The part 3 is about humanoid. The last 5 years of my university work is devoted to developing humanoids. The reason, reason one, humanoid is an ultimate target to integrate all aspects of robotic functions: perception, manipulation, mobility, intelligence of all kinds, communication with humans, and energy and structure. All of them must be embedded within the limited size, weight, and shape. The reason to create anything which we need is the policy of JSK. JSK is a laboratory of myself, JSK management. We have developed and accumulated all the necessary technology by ourselves. All the technology was transparent. Therefore, we can change everything to integrate as we want. And the last 5 years, I think it was a time to integrate them to build a humanoid. Because without this opportunity, I have no chance to build humanoid in my research life. Therefore, the last 5 years were devoted to humanoid, and this is also a little bit older my son, one of my sons. And this is dynamic humanoid. Year by year, we developed much kind of things, H6 and H7 and so on. All the machines is designed by our students, and every program, vision, control, everything is done by. One of the motivation why I started the humanoid is almost at that time, Honda announced the humanoid systems. When my student looked the Honda's P2, the shocking humanoid studies, my student want to build humanoid by themselves. So they asked me to have a plan to build humanoid. I decided to do because most of the component, the control system and vision system and intelligence communication, everything is done by remote brain approach beforehand. So just the difference is not the remote brain system, but real embedded computer systems. So it is not so difficult to develop. Honestly, it takes about 1 year to complete it. This is 2001. Mark Raybert visited my laboratory. He has no appointment. He called me one day, and I am now in Tokyo. I heard you built a humanoid robot, so can you show me? Then he came, and he tried to make the joystick control. I think he's a very good driver. By moving the joystick, he can move the humanoid, very dynamic work like this. Oh, changing a little bit. So this is the guy who developed Kagami-kun and Nishiwaki-kun. He did not control robot like this because they sometimes afraid to fall it down, but Mark didn't. And 2002, it was just after the 9/11, and at that time, the Davos, New York, was Davos meeting is not Davos in Davos, but in New York. Rodney and suggested me to join this Davos meeting, and at that time I brought this movie. This is the robot system. Find the pink ball and try to catch and take it. But my student is not so kind enough. So he comes and to move another way. In such a way, using some visual and motion interactions, we can, human and robot can interact inside my laboratory. This is a very rough history of my research on my life. This is my graduate study, and after then I joined to the electrotechnical laboratory, MIT, and after moved to university, my student did many kinds of things. One is the manipulation and programming system, intelligent software, and the vision system, and everything is integrated into those systems. And after that, my student knows my first work is turning a crank in 1969. And when in Japanese university tradition, when retiring, I have a final lecture. I did in March 2004. I did the final lecture at the university. At that time, my student had a secret presentation. This is a movie of that. I didn't know this kind of secret project. My student knows my first work is a turning a crank 42 years ago. But after the completing this human robot, they let humanoid to turn the crank much better than my PhD work. He's turning like this. So I felt very, very happy because this kind of operation of the humanoid turn the crank, that is a very good present for my retirement lectures. So, in part 4, so far I talked about the research myself and the university environment, and furthermore, I have also appointed the project leader of a national project. One is a national project of human R&D, and this is the machine which is made by the Kawada Industries for the human robot project of the METI sponsored. And by this, from 1998 to 5 years project, total budget is about $50 million, and development method, develop platform. And using this platform, many kind of applications can be done. So I think this is a platform which can be on market now. And some of the experiment is here. So the vision system recognizes this plate and collaboration with humans. Bring together by using, he's now looking down and recognizing where the panel is, and to make all the panels and carry together with the human. So that is also compliant motion is needed. The motion is guided by humans by force feedback. And also another approach is done by interesting things. This is a robot, not a people, human. Humanoid is riding on the machine, and it is controlled. And this is this guy is controlling the humanoid, and the humanoid controls the machine. That is one of the concept to make any kind of machine will be controlled by humanoid. That is one example. The performance is not so good enough, but we have tried this kind of things. And another big project on national level is the Expo in 2005. 7 years ago, we have the Expo in Nagoya. At that time, METI, Ministry of Economy, Trade and Industry, or something like that, was decided to give the robot exposition. And this is the prototype. One of the prototype motion is we called for the robot development for the Expo for 2 weeks. And from 300 applications, we choose 65 demonstrations, universities and companies. And the result is shown in the exposition. I think somebody of you have experience of this robot exposition, but I was asked to make the project leader of this, and I enjoyed it very much. But I enjoyed. But the 65 team suffered to create it for this demonstration. There are many kinds of robots which we support for future town in many kind of robot will be introduced into the society. So the park areas or some hospital and also the home and so on. So many kind of robots is prepared and demonstrated. I think I will skip it. 3 years ago, Japanese government high-level committee of space development launched a special working committee for feasibility study of moon exploration by robot. I was involved as a committee member, and I proposed of sending humanoids on moon for exploration. From the standpoint of robotics, I attempted to make a possible plan to send a humanoid on moon. The major purpose of my proposal is to create novel machines, novel means for space exploration. And then I expected the new technology could be brought down to the Earth for our future life. When I was investigating some possibility of the humanoid on moon, the most severe condition is the environment. The physical condition on the moon is extremely severe, not only for human, but also for machine design. The surface temperature is 120 degrees Celsius in daytime and minus 170 degrees at night. Atmosphere is all vacuum, no air. As you know, no air environment causes severe problem for heat transfer and tribology. So conquering this kind of thing is very, very difficult than creating human intelligence and control. By the way, there is a myth. The component of space machine need to develop extremely special, but I didn't agree. I propose to solve this problem by robot wearing space suit. Space suit divide world in two. Outside the space suit is the moon. Inside the space suit is the environment of Earth. So therefore, controlling the inside the space suit, almost the temperature and also the air can be controlled. By using this, most of the component on the conventional component can be used, even in the space. That is the one idea, and I also tried to make the design, modular design, and the remote blend approach is good because the main computer is protected from the moon environment, and just only small computers on board on the humanoid, and communication by the radio link makes the remote brain approach, which I did in my laboratory, and software platform. And another point is this one, self-protection by space suits, and also super reliability concept is needed. If a robot can repair by themselves, we put 3-4 humanoids on moon, then each other, they can, if some damage is occurred, then they can replace parts. By using that, the reliability improves very much. The study is done, but the government do not have enough budget to do it. After then, we have a very severe economical condition now. So the sending human on the moon cannot be done. And I am proposing the grand challenge. Robot now is like this. Many kinds of robots now, manufacturing, service, life support, entertainment, personal mobility, and remote X. This is the current robot. And using the humanoid, we have this kind of this is Professor Inoue's laboratory. The three humanoids is cooking and washing and so on. This is just taking this kind of operation. They have the complex dexterous action is done by. And right now, most of the experiment is done by like this. The humanoid can recognize and recognize the very complex terrain and make a plan and to move in real time. So right now, the humanoid can not only the flat space, the pebbles, and also the different positions. And I think this kind of. Also, this robot can walk even on the sand because it is necessary for sending humans on moon. Moon is covered by the rigorous, very fine sand. And another new current performance of Japanese robot is a new ASIMO, which is developed on the last November. This is right now the most advanced performance of the Honda ASIMO, jumping and running and so on. The running speed is 90 kilometers per hour. So when I cannot run for so long time. 9 kilometers per hour is very, very, and also kicking the ball, very powerful. So maybe some World Cup or something. And this is not only the kicking, running, jumping, but also they have the very dexterous hand to turn it on and take it off. Not dexterous enough, but it does. So making some, of course, this is sensed by the vision system, and to detect and to make the So when I was invited last November for celebrating Gelthirdingers, they had the DLR symposium. And at that time, I proposed this grand challenge, robot fleet for emergent response. I think this is very important for us. And the robot fleet for emergent response on severe accident or disaster. Robot fleet, many kinds of robot. The small helicopter or running or humanoid, and that for special purpose, using this. If some severe accident or disaster, then every robot can gather and go to recover that situation. I recognize the challenge to humanoid as a very good technology-driven project. New parts, new theories, and new system architecture can be tested in those challenges. 15 months ago, Japan had a huge disaster of earthquake and tsunami. And as you know, it destroyed Fukushima nuclear power station. At that time, people cannot reach access to the place as it is too severe environment. So the accident becomes very bad. If we have a robot that can go into the severe environment, things must be changed a little bit. So many people wanted to do it by robot, but we didn't prepare any robot yet at that time. Accident and disaster also exceed our estimation. Thus, it is difficult of 100% preparation beforehand. In order to measure such unexpected severe situation, we need to have universal robot that work as a human agent. It is not too late to begin human project for severe accident measuring. It is a reason to propose these challenges. So in that case, develop surrogate or avatar that work in severe environment as human agent in case of emergency or severe accident. That will consist of two things. One is an innovative cockpit for remote maneuver, plus smaller, stronger, and flexible humanoid. Task of environment is like this. In case of severe accident, chemical or nuclear plant, reconnaissance, emergency measures, restore service, and operation would be like this. And the topics and the challenge for this challenge is like this brain-computer interface for the novel cockpit and this kind of things. And also topics is the cloud robotics, motion planning, SRAM, and so on. And I think smaller and stronger body is needed because it must go into narrow space. So I think 80% in size, but power is needed more than 150% of adult. And complex and flexible whole body motion and dexterous and power manipulation is needed. Tasks to be challenged is traverse, compound a destroyed route, create own walkway, bring and climb a ladder, move heavy objects by lever, tumbling, sliding, and rolling big objects, use of tools, replace machine component, and drive utility machines or construction machinery, and in such a way, want to make a new scheme for humanoid. I think the surrogate or avatar of humanoid is something like this, tele-X innovation. Several hundred years ago, telescope, then telephone, and we can talk with remote place. Television, we can view from remote place, and telepresence, it is now on market. And then teleaction, the very smooth action from teleoperated system will be the new innovation. So I think the proposals which I did, this would be done, tele-X. And the topics is realizing this humanoid, and also the real cockpit. So, and many of you know, very recently, DARPA announced some grand challenge, robotics challenge. Scenario of DARPA robotics challenge, I think it echoes my proposals at the last November DLR. The scenario is like driver utility car like this. So all of the things, all of this scenario must be done single machine. That consequences the humanoid systems. So I think, you know, so I think by proposing this grand challenge, if I was younger than current time, I will definitely challenge to do this kind of humanoid. I think DARPA's robotics challenge is very important for not only for military use, but I think it is a benchmark of the robot system. And also, I suppose it gives some paradigm change for the development of humanoid, because that is clearly important actual issues for required operations. Thank you very much indeed.